Okay, so what we're going to do in this section now is we're kind of going to do things that are very similar to chapter 2, except we're going to use the idea of the unit circle. So let's first start off by defining what a unit circle is. So a unit circle is a circle centered at the origin with a radius of 1. So if you think about it, when I say we're going to work with the unit circle, we're literally going to use the idea of creating angles moving along a unit circle to determine kind of our trig functions. So to kind of also talk about the equation of the unit circle, so we would say that the general equation of a circle with a center at h comma k and radius r is given as the following: x minus h squared plus y minus k squared equals to r squared. So this is a generic equation of a circle, right, where it's centered at h comma k and the radius is r. So for our case, for the unit circle, so the unit circle has an equation of x squared plus y squared equals to 1. And this is what we mainly care about, okay? So, and notice how it becomes this, because what do we know about h and k? Well, if my center is at 0, 0, it's at the origin, and the radius is 1, you replace h and k with zeros and r with 1, you get that, okay? So what we're going to be doing is we're going to be using this equation to help us find points on the circle, as well as answer some questions that involve trigonometry. So this equation may be used to find points on the circle. Okay, so with that said, let's look at our first example. And for example 1, we have find a point on the unit circle given x comma 1/2. Okay, so if we look at this, we're saying we know that the x value could be anything, and notice how it's saying find a point. So there is going to be more than one point, and we're just asked to find one of them. But what is it that I know? If we're on the unit circle, this equation applies. We know the y value must be 1/2, so I'm going to take the equation of a unit circle and I'm going to replace the y with 1/2 because that's what we know, and then we're supposed to find the x value. So this turns into x squared plus 1/2 squared equals to 1. Now if I solve for x, I get x squared plus 1/4 equals to 1. If I subtract 1/4 from both sides, I get x squared equals to 3/4, and then if I square root it, I get x equals to plus or minus rad 3 over 2. So, and since the question is saying find a point on the unit circle, you could use any one of them. But technically speaking, there's two of them that yield to that y value of 1/2, which we could put plus or minus rad 3 over 2, comma 1/2. Right? So it doesn't matter. You could use both, but as long as you just give one of the two at the very least, we're okay with it. Okay? So now let's also talk about symmetry of a unit circle. Okay, so symmetry of a unit circle. So we're going to say consider a, let me move this up. Consider a unit circle. And let's just draw it out. So what is it that we have? We have this unit circle. Remember, it's centered at the origin and the radius is 1. Okay, so I guess based on this picture, there is a question that I would want to ask. The question is, what is the unit circle symmetric to? And in fact, if you notice, this unit circle is symmetric. Symmetry means what? I could divide it in half. So it's symmetric, in fact, to the x-axis, because notice how I could reflect it about the x-axis and I get the same point. So we can basically say it's definitely symmetric with respect to the x-axis. Now, what is it that we know? If it's symmetric with respect to the x-axis, we would say, look, if the point A comma B is on the circle, so is A comma negative B, right? Because if you look at this, what do you notice? Their x values are the same, but their y values are exact opposites. What else do we know? It's also symmetric with respect to the y-axis. So y-axis, if A comma B is on the circle, we can then say so is negative A comma B, which basically we're saying the x values are opposites. And then lastly, it's also symmetric with respect to the origin, which means if A comma B is on the circle, so is negative A comma negative B. So the exact opposites, like they're across. So we could also say it's symmetric with respect to the origin. And with this, we would say if A comma B is on the circle, so is negative A comma negative B. All right, so that's what we're saying. So what we notice is, in fact, the circle is pretty much symmetric to everything, right? Because we get all three conditions are satisfied, okay? So moving on to our second example. So for example 2, we're going to say verify that negative 3/5 comma negative 4/5 is on the circle, is on the unit circle. And then once you do that, I'm going to say then use symmetry to find 3 other points on the circle. 3 other points on the circle. Okay, so this is actually going to be pretty straightforward, because I think what we're going to do first is we're going to show that this point is on the unit circle, and if it's on the unit circle, what does that mean? This equation, x squared plus y squared, has to equal to 1, right? Because if this is the equation that describes the unit circle, then if this point's on the unit circle, then when I replace x with negative 3/5 and y with negative 4/5, and I simplify it, I better get it to equal to 1. If not, then it's not on the circle, right? Because this is what's saying, hey, every point that's on the unit circle satisfies this equation. So if to verify it, we need to plug in negative 3/5 for x plus negative 4/5 for y equals to 1. So let's see if that's true. Negative 3/5 squared becomes 9 over 25, plus negative 4/5 squared is 16 over 25, and 9 over 25 plus 16 over 25 is 25 over 25 equals to 1, which notice how that shows 1 equals to 1. So clearly we just showed that this is true. It checks out. The left side does equal to 1, so it is on the unit circle. Now we're told to find 3 other points that are on the circle, which remember we just talked about symmetry. It's symmetric with respect to the x-axis, y-axis, and the origin. So if you think about it, if we go off of the x-axis, if negative 3/5, negative 4/5 is on the circle, what else is on the circle? Negative 3/5, comma 4/5, right? Because those are opposites. Now, it's also symmetric with respect to the y-axis. So if this point is on the circle, then so is 3/5, comma negative 4/5. And lastly, since it's symmetric with respect to the origin, negative 3/5, comma negative 4/5 is on the circle, which means 3/5, comma 4/5 is on the circle. So those are the other 3 points we found through symmetry. Okay, so the next part of the notes hopefully are going to be review. So this is good news, right? Because we're starting to see things in trig that are very repetitive. So our goal now will be to find exact values of trig functions using a unit circle. So if you remember, we found exact values of trig functions. The only difference now is we're going to use the unit circle. So the only thing I want to point out to you is that keep in mind that for a unit circle, R is always 1. So remember, we're going to identify the x, y, and r. Now, why is r always 1? It's because it's a unit circle. Its radius is 1. So r is going to be 1. So when we find the x, y, and r, we know that our r is always 1. So we have to work backwards. Since we have r is 1, we need to find x and y. So, in other words, we will use r to help find x and y. Okay, so now let's actually write this stuff out. So here are the steps. So what are the steps we need to follow? And the steps that we need to follow in finding exact values, this is pretty much review. So the notes that I give you now, you've taken them before. So I'm just going to give them to you anyway, just so you see how it's literally the same thing. It's very consistent. So steps in finding exact values of trig functions. So and this is for a unit circle, but you'll see how the steps are the same. It's not going to change. So for step 1, if you remember, what's the first thing we did? We draw the angle in standard position. Okay, except we're going to be moving along the unit circle. And then if you remember, what's the second thing we did? We identified the reference angle, because remember, the reference angle was the most important part. Identify the reference angle. And one other difference is, which I'll show you shortly, we're also going to be working in radian measure. Now in radian measure, actually, it's a lot easier to identify reference angles in radian measure. Just by looking at it, I could tell you what the reference angle is. Okay, so 3, then we're going to basically create a right triangle from the unit circle to the x-axis. If you remember this one, in the past I said, hey, pick any point on the terminal side and create your right triangle. Now we're forced to start from the unit circle and go to the x-axis to create our right triangle. And then for for 4, the last step is using r equals 1. We're going to find x and y, and then we can, after that, we can state our exact values and state the exact values. So hopefully, like I said, you were able to, this stuff is fairly familiar because it's literally review. Okay, now before we do some examples, I want to now go ahead and tell you how you could find reference angles for radian measure, because this is going to be very nice and convenient. So reference angle for radian measure. So we're going to say if we have an angle in radian measure of the form a number pi divided by a number. And what I want to point out is these numbers that I'm talking about, these numbers have to be integers. Okay, so we can't have these numbers be decimals. They have to be integers, okay? And they have to be in simplest form. What do I mean by simplest form? You have to simplify them where you can't simplify anymore. So, for example, 6 pi over 4, that's not in simplest form because I could still simplify this, right? Because this simplifies to 3 pi over 2. Now it's in simplest form. So that's what I mean. Okay? So if they're in simplest form, so we have it of this form and it's in simplest form. Now let me show you how we could easily find the reference angles. So if we have a number pi over 6. So remember, this is in simplest form, and we have an integer pi over 6. And if my number in the denominator is 6, then this has a reference angle of 30 degrees, or pi over 6. Okay, so this is what I'm basically saying. Anything pi over 6 has a reference angle of 30 degrees, which is nice, right? So these are like very quickly, you could see just by looking at it what it is. So if I have a number pi over 4, this has a reference angle of 45 degrees, or we call it pi over 3, or sorry, pi over 4, not pi over 3. Okay, and then last, or the next one is negative. If we have a number pi, not negative, right? This is just a number pi. We don't care. It could be negative. We don't care about the sign as long as it's an integer pi over 3. This has a reference angle of 60 degrees, or pi over 3. Right, so this is what's nice. Anytime you have pi over 6, 30 degree reference angle, pi over 4, 45 degree reference angle, pi over 3, 60 degree reference angle. Now, if we have something like a number pi over 2 or a number pi, then these are going to be quadrantals. These are quadrantals. Okay, so with that said, we'll do 2 more examples and then that'll wrap up this section. So for example 3, we're going to say find the reference angle of 11 pi over 3, then find the associated point, which has coordinates x comma y on the unit circle. Okay, so I think what we need to do is we need to first find the reference angle, because obviously that's going to help me find what or what kind of help me find the points, and then I need to figure out what quadrant it lands in. And then I'll really quickly show you just by radius. Like, a lot of people convert this to degrees and then they figure out what quadrant it lands in. I do it differently. I'll show you how I do this in my head, but I'll write it out, but I kind of do this in my head because the denominator pretty much tells the story. So here's what we know. What's the reference angle of this? Since it's a number pi over 3, and that's in simplest form, I can't simplify that anymore. The reference angle is what? 60 degrees. Okay, now I need to figure out, hey, which quadrant does this land in? Okay, now if I'm trying to figure out the quadrant, we would say, look, so for the quadrant, what I do is I say find the closest whole number pi to 11 pi over 3. And the way I think of it is, since this is a pi over 3, I'm going to start with 11 pi over 3, and this is what I do in my head. I just keep adding pi over 3 and subtracting pi over 3. So look, if I add pi over 3, what does that give me? 12 pi over 3, which, by the way, what is 12 pi over 3? That's 4 pi, isn't it? So this is the closest, well, is this the closest whole number pi to 11 pi over 3? Let's see, if I go the other way, now if I go to the left, I'm going to subtract pi over 3. So if I subtract pi over 3, 10 pi over 3, not a whole number. And then subtract another pi over 3, 9 pi over 3, that becomes 3 pi. So 11 pi over 3 is between 3 pi and 4 pi, but it's closer to 4 pi. So how do I know which quadrant 11 pi over 3 lands in? Well, let's draw the unit circle. What do I know? Every time I go half a circle, that's pi. So what we know is 11 pi over 3 is very close to 4 pi, but it comes up a little short of 4 pi. So if it comes up a little short of 4 pi, and 4 pi would be what? Pi, 2 pi, 3 pi, 4 pi, it would land here. And 11 pi over 3 comes up a little short of 4 pi. That means it'll be in quadrant 4. Okay? So this is in quadrant 4, and I need to find the coordinates for this point. And what do I know about the reference angle? We know the reference angle is 60 degrees. So if I make my right triangle, notice how I have my 30, 60, 90 triangle, which now it's going to go back to what we've learned about 30, 60, 90, except my radius is 1 now. So I have the hypotenuse. Now to go from the hypotenuse to the shorter leg, I divide by 2, because remember, from shorter leg to hypotenuse you double, but now I'm going backwards. And then to go from the shorter leg to the longer leg, I multiply by rad 3, so that's rad 3 over 2, except since I'm going down, it's negative. So the coordinates of this point are 1/2 negative rad 3 over 2. Sorry, this is a negative rad 3. Maybe I should write it bigger. So the coordinates of this point are 1/2 comma negative rad 3 over 2. And I found this just by literally using my reference angle and the idea of 30, 60, 90 triangles, and that's all it was. The only difference was, though, for a unit circle, your hypotenuse, your r is always 1. So where, if you remember in the past, we'd start with the shorter leg, but this time we can't pick any side. R is given to us. Okay, so let's do one more example where we'll be finding exact values of trig functions, and that'll basically do it. So if we look at this example, example 4, find the exact values of A tangent of pi over 3, B sine of 3 pi over 2, C cosine of negative 3 pi over 4, and D cosine of 5 pi over 6. So let's start off with the first one. So I'm going to start off, and we're using a unit circle, by the way. So pi over 3, what do I know? That's actually a little bigger than 0 because it's closest to 0. And we know since it's pi over 3, once again, that has a 60 degree reference angle. Maybe I should make my circles bigger. But this becomes, the reference angle is 60 because of the pi over 3. So this is, let me make a bigger circle. I'm going to do it down here. So we have a circle, and we said it was pi over 3, so this is 60 degrees. and then we draw our right triangle. So notice how nothing is different except r is 1. So now I go backwards. If I have the hypotenuse, I could find the shorter leg by dividing it by 2. I could go from the shorter leg to the longer leg by multiplying by rad 3. So I get rad 3 over 2. So then coming back to this tangent is what? Y over x. So tangent of pi over 3 is y over x, which is rad 3 over 2 over 1/2. Which then if you simplify this, you get rad 3 over 2 times 2 over 1, which is rad 3. So hopefully you see that this is literally the same thing. Now, sine of 3 pi over 2, now notice how this is 3 pi over 2, which is a quadrantal. Remember, if we have a something pi over 2 or just a whole number pi, it's a quadrantal. And what do I know? Each distance I move along is 90 degrees, or it's pi over 2. So this is 3 pi over 2. So if I start here, pi over 2, 2 pi over 2, which is pi, 3 pi over 2, which puts me down there. Now, if you remember, for quadrantals, r is 1. We don't make right triangles because we can't. But the coordinates of this point are very easy to find, because what is that? The x value is 0, the y value is -1. So sine of 3 pi over 2 is what? It's y over r, so it's -1 over 1, which is just -1. Okay, so now you might want to pause this and try to do the other two on your own, and then press play again. But I'll do C over here off to the right side. So once again, let's draw our circle, our unit circle. And then what is this saying? -3 pi over 4. So once again, since it's pi over 4, I know the reference angle is 45 degrees. Now, since it's negative, all that's saying is I'm going to rotate clockwise. Now look, -3 pi over 4 is going to come close to negative pi, right? Because remember, I'm doing that in my head. What's the closest whole number pi this comes to? And -4 pi over 4 is the closest it is, which is negative pi. But -3 pi over 4 comes up a little short of negative pi. So I'm going to rotate, which means if this is negative pi is here, -3 pi over 4 comes up a little short, which ends up here. So this is my point. And we know that since this is pi over 4, it has a reference angle of 45 degrees. So we draw our right triangle. We have a 45, 45, 90 triangle. My hypotenuse is 1. So then how do I get from the hypotenuse to the leg? If it was a 45, 45, 90, to the leg, to the hypotenuse, we would multiply by rad 2. But now what do? We divide by rad 2. So this is 1 over rad 2, 1 over rad 2. And since I'm going to the left and down, these are negatives. And you could even rationalize them and call them negative rad 2 over 2. It doesn't matter. So then cosine is what? Cosine is x over r. So cosine of -3 pi over 4 is x over r. So it's -1 over rad 2 over 1, which is -1 over rad 2, and if I rationalize it, it's negative rad 2 over 2. Okay, now to do part D, literally we're going to do the same thing. So let's draw this out. So this is D. Let's draw the circle large enough. And let me move this so you could see it. Okay, and what is it that we're trying to figure out? Cosine of 5 pi over 6. Now look, before I draw this angle, since it's of the form of a number pi over 6, my reference angle is 30 degrees. And notice how this comes up just short of 6 pi over 6, which is pi. So this comes up just short of pi. So pi would be a half a circle. So this comes up a little short of pi, which puts us there. Right? And this we know is a 30-degree reference angle. So I have a 30, 60, 90 triangle. The hypotenuse is 1 because it's a unit circle. Now the shorter leg, which is opposite the 30 degrees, is a half because I just divided by 2. And then the longer leg would be rad 3 over 2, but since I'm moving to the left, I'm going to call that negative. So cosine of 5 pi over 6 is x over r, which is negative rad 3 over 2 over 1, which is just negative rad 3 over 2. Okay, so, and that takes care of this one. So this pretty much takes care of the notes. Hopefully you saw how similar this section was to previous sections, except my angles now that we're working with are in radian measure. But remember, we still care about finding the reference angle, and then we care about finding x, y, and r. And the only other difference was the radius over here was always 1 because we're working with a unit circle.